Let me make sure that you all saw a couple of announcements that I emailed to you. So due this Wednesday, which is 2 days from today, I would like you to please sign up for the online forum for the course. And I emailed you instructions about this. And it's very important that you email me the username that you chose so that I can let you in. And then I would like you to email me your photo and short bio for the website. Question?
Would you like an updated bio and photo from our matrix class?
If you would like me to use the same one as last year, if you took my matrix class, then just let me know and I'll recycle it. And I already posted the first homework, which is going to be due next Wednesday. So you can find it on the course website. I put some instructions there, but I wanted to be clear to you that not only are you allowed to work together, I really would encourage you to work together on the homework. But then you really have to write the questions on your own, write down your solutions on your own. And in each question, I ask that you please tell me who you worked with. It's fine, talk to as many people as you want, but just write down your own solutions and tell me who you talked to. Okay? Any questions about it? Okay. Let's talk about. So last time I told you a little bit about the symmetric group S3, and I told you that it was a very good example of a Coxeter group, but I still haven't told you what a Coxeter group is. And so that's my goal for today, is basically to tell you what a Coxeter group is, and then give you some other examples of Coxeter groups. So today we will talk about Coxeter systems. So to build a Coxeter group, you're going to start with something called a Coxeter matrix. And so this matrix is going to be S by S, so the rows and columns are going to be indexed by some set S. The entries of the matrix are going to be either positive integers or infinity. This matrix is symmetric. You have to have ones down the diagonal. Okay. So the matrix, the entry S comma S is always equal to 1. And the entries off the diagonal cannot be equal to 1. So we're going to start with a matrix like this, and we're going to build a group out of it. Now, associated to this Coxeter matrix, we're going to associate a Coxeter diagram. Okay. So this is going to be a labeled graph. So I'll tell you how to do this. Coxeter diagram of M. What we're going to do is build a graph where the vertices are labeled by this set S that indexes the rows and columns. Okay. And then I have to tell you what the edges are. And the edges will basically, you're going to put an edge or not depending on what entry you see in the matrix. Okay? So given vertices S and S prime in the graph, you have to decide whether to put an edge there or not, and that's going to depend on the entry in the matrix. So if that entry is equal to 2, then you don't put an edge. If that entry is equal to 3, then you put an edge. And then if the entry is bigger than 3, then you're going to put an edge on the graph, and then you're going to label it with this number m. Okay? So let's do an example real quick. So here's a Coxeter matrix. It's going to be 3 by 3. I'm going to index the rows and columns by the set S1, S2, S3. And the stipulation is, first of all, I have to put ones down the diagonal, right? Okay. And then I have to choose the other entries. They should be either positive integers or infinity. In any way, this just better be symmetric. That's the only condition. Okay. So for example, I might put a 3 here, then I have to put a 3 here. If I put a 2 here, I have to put a 2 here. If I put a 4 here, I have to put a 4 here. This is a Coxeter matrix. And then I build the Coxeter diagram out of this. Okay. And the way I do it, I just basically make a vertex for each one of the labels of the rows and columns. And then I see, OK, well, between S1 and S2, the number is 3. So that means I should put an edge between S1 and S2 and not label it. Then I see a 4 between S2 and S3. So that means I should join S2 and S3 and put a 4 here. And then between S1 and S3, I look up and I see that the entry is 2. And that means that I shouldn't join them by an edge. Okay? So this is the Coxeter diagram corresponding to this Coxeter matrix. Okay? So far, this is a very free construction. You just choose this in almost any way that you like. And with this data, we're going to build a Coxeter group. So this defines a Coxeter group. So how are we going to make a group out of this? What we're going to do is define it by telling, I'm going to tell you what the generators of the group are and what are the relations between them. Okay? So the generators are just going to be, we're going to have one generator per vertex of the diagram or per row of the matrix. Okay? So the generating set is just the set that we're using to label S. And then I just have to tell you what the relations are between these elements. And you might guess what these look like by the construction from last time. These relations are going to look like this. For each S and S prime in S, in big S, I'm going to make a relation that if I raise S prime to the power of the number in the matrix, M of S comma S prime, I get the identity. Okay? So these are the generators and the relations of the group. So let's go ahead and write down the group for this Coxeter diagram. Okay. So the Coxeter group that we get here is generated by S1, S2, and S3. And it's subject to the following relations. I didn't write that this is for all S and S prime in big S. Okay. So what are some relations? For example, what happens if you choose S and S prime to be the same element? Well, that counts. And you know that if S and S prime are the same element, then the entry of the matrix is equal to 1. So what this says is that S squared is equal to E for each one of the generators. So S1 squared is equal to S2 squared is equal to S3 squared, which is the identity. Okay? That's what I get from this one. Let me move over here and let the camera catch up with me. That's what I get from this one. S1 squared equals 1. S2 squared equals 1. S3 squared equals 1. Now I'm going to go here and see what is this 3 telling me. I get a relation that says that S1, S2 cubed is equal to 1. Okay. S1, S2 cubed is equal to the identity. And also S1, S3 squared is equal to the identity. And also S2, S3 to the 4th power is equal to the identity, and that's it. Okay? And so my Coxeter group that I get is generated by S1, S2, and S3, subject to these relations. Okay? Is it clear how I put this group together? Any questions about it? So let me point out some things about this construction. Maybe the first one I'll point out explicitly is that S squared is equal to the identity for every generator. Okay. I want to make that explicit. You're always going to see this in any Coxeter group. There's one thing that I haven't quite told you how to deal with, which is what happens if you have an infinity in the matrix. So the way you should interpret that is that if you see an infinity in the matrix, then this is going to mean that S and S prime have no relation between them. Okay? So you don't have a relation of this form. No relation between S and S prime. Okay.
Federico, does that mean that the two would not appear in the same expression?
Well, they can appear in the same expression. But for example, you know that if you have an expression and you see S1, S2, S1, S2, S1, S2, then you know that you can cancel that by this relation. But if this entry is infinity, then that means that if you have SS prime, SS prime, SS prime, no matter how many you have, you can't cancel that. There's no relation of that form.
That would just be the string, whatever it is, it's changed.
Right. What this means is that there is no rule that allows you to cancel an alternating string of S's and S primes.
So SS prime is of infinite order, is that the same?
Exactly. That's exactly the same thing as saying that SS prime has infinite order in the group. Let me point out something else. This should look a little bit different from the relation that I introduced last time between A and B. The relation that I wrote was ABA equals BAB. But the reason for that is that, well, if I have a relation like this, then this is going to be equivalent to a relation like this. S, S prime, S, S prime, S, etc., where there are m things here, is equal to S prime, S, S prime, S, S prime, S, etc., where I have m things here, m things here. So I claim that these two equations are equivalent in the group. Yeah, I mean, I'm just saying if this equation holds for S prime elements of the group and m some positive integer, then this one holds, and vice versa. These equations are equivalent. And so the equation that I wrote last time, ABA equals BAB, is equivalent to having told you AB cubed equals E. Okay? Let's talk about this in the form. So think about why that's true, and tell me in the form why this is true. Okay? But so these are two ways that are equivalent of thinking about the same relation. Okay. Okay. So, having given these definitions, then, well, I'll tell you what a Coxeter system is. A Coxeter system is basically a group W together with a set of generators S of this form. Okay, so, a Coxeter system is a pair W comma S of a Coxeter group W and a set S of generators of this form. Yeah. A Coxeter system is the pair, so I have to specify the group, I have to specify the generators. You'll see that I ask you exactly that question in the homework. I'll say that in a second. I'll say that in just a second. Now, how should you think about these Coxeter groups? Let's talk about it. I mean, this is the construction. How do you actually play with these things? Well, you should think that the elements of W are just words in this alphabet, S. Okay? So to give you a word, I just tell you some sequence of words in the generators. Sorry, some sequence of letters are words, something like S1, S2, S3, up to SK, where these guys are generators. Okay? Finite words. This is important.
And then you don't mean that S1 necessarily is different from S2.
No, I didn't say that. I didn't say that. These could be equal. There could be repetitions, no repetitions, whatever you want. Now, how are you supposed to parse these relations? Well, the thing is, these relations allow you to operate on words without changing the group element. So let me say what I mean by that. So the elements of W are finite words of this form subject to the equivalence relation that allows you to do the following. If you have some big word, if you have some word, so here's a word, there's some U, and then you see inside the word you see S, S prime, S, S prime, S, S prime, with each one of these guys appearing M of S comma S prime times. In other words, I have two M of S comma S prime letters. So if you ever see this in the middle of a word, then you're allowed to cancel it and get the same word. I mean, get a different word, but that represents the same element of the group. So when you see this, you're allowed to cancel this stuff and get an equivalent, get a different expression for the same element of the group. And the other way around. If you have a word like this, you're always allowed to open it up and insert an expression like this in the middle, and you get the same thing back. You get the same element of the group. Okay? And so the elements of the group are just these equivalence classes of words. And the operation of the group. So I told you the elements. And to tell you the operation, well, the operation is just take two words and glue them together. Operation is just gluing words. I'm claiming that this defines a group. So far, I define the elements, I define the operation, but I can't just tell you that. I mean, we have to really make sure that this is a group, right? So what do I need to check to make sure that this is a group? Well, basically, we know that a group has to have, elements, operation, and two things. We need a special element called the identity, and we need for every element of the group, we need an inverse. Okay? So what's the identity here? Well, the identity is the empty word, right? Which we're going to call E, because it's the identity. Yeah, if you have some word, and if you append nothing to it, then you get the same word back, no matter whether you append it to the front or to the back. So the identity is just the empty word. What about inverse? So what is the inverse of some word like S1, S2, ... SK? I should have an inverse if this is a group. Well, you have to think about it for a second, but you'll see that if I flip this word, that's exactly the inverse. Why is that? Because if I multiply these two words together, then I'm going to see in the middle SK. Well, let's just go ahead and do it. S1, S2, up to SK minus 1 SK. I'm claiming that this is the inverse of that. Actually, there's another thing that I should have said. This operation better be associative, right? But it is, right? You're just gluing words, so it doesn't matter what order you glue them in. So this operation is associative, and now I have to perform this computation and make sure that I get the empty word. Well, that doesn't look empty. But the thing is that we have this equivalence relation that allows me to say, okay, well, I see SK squared, so I cancel that. And I get S1, S2, ... SK minus 1, SK minus 1, ... S2, S1. And now I see SK minus 1 squared, so I can cancel those. And I keep doing that until I get S1, S1, which is the identity. Okay. So that's why this actually is a group. Now, here I'm describing it a little bit informally, and I would like to formalize exactly what it is that I'm doing here. So formally, what I'm doing is building a Coxeter group by saying that I'm going to build it as a quotient group. Okay. So basically, I take the free group generated by S, and then I mod out by the relations. And the way to do that is to mod out by the normal subgroup generated by the relations. Okay. Now, feel free to take whichever one you're more comfortable with. I mean, maybe this is a good, pleasant way to think about it psychologically, and think that this is the mathematical construction that you're doing. One of the exercises in the homework is to parse this definition, understand what it says, and prove that it is equivalent to two other definitions. So
the freest group we can get here is if our matrix has infinity everywhere off the diagonal.
exactly. So for example, if my Coxeter matrix has ones in the diagonal and infinities otherwise, then that's kind of the freest possible Coxeter group that I can get with these generators. The only relations that I'm going to have is that the generator squared is equal to the identity, and nothing else. Okay.
That's a nice group.
Yeah, I mean, it's the freest Coxeter group. It's very nice, no? It is, and I will say more about how this is a very nice group. Okay. So I don't know about you. I prefer thinking about it in this way, as equivalences of words. So let's do some examples of Coxeter groups. So here's one example. I mean, you saw the way I specify a Coxeter group is by giving you either a matrix or a graph. So here's a graph. It has one vertex, which is called S. Okay. Well, that's a very simple group. I mean, that defines a very simple group. It's just generated by this guy subject to the relation S squared equals the identity. Okay. But if you think about this, this group has only two elements, the identity and S. It's the group of two elements. There's only one. That's a Coxeter group. Okay. Now, what about this one? Let's draw this graph. Then what we get is generated by S1 and S2, subject to the relations that S1 squared and S2 squared are the identity, and also S1, S2 cubed is the identity. But I told you that this is equivalent to saying S1, S2, S1 equals S2, S1, S2. And so we saw last time that this is the symmetric group, S3. Symmetric group, S3. Yeah?
Federico, where do we get the cube there? Where does the cube come
Oh, because remember that when I don't label an edge, then implicitly it has a label of 3 in it. I erased that, but whenever you don't see an edge, that means there's a cube.
So you didn't say before, like first you just showed us the matrix and then you drew the diagram and then you didn't do anything with it. So you're saying that normally you'll just draw one of these graphs that's labeled and then you can suck all the information from there? So the point of this?
Yeah, I mean, it's shorter to draw the diagram than to draw the matrix, and the information that they contain is the same. So generally, I will specify the diagram and not the matrix, and that's what people do normally.
This freest group is just copies of C2.
No, actually. Well, actually, let's talk about two other groups. So what is the freest group that Aaron was talking about? Well, it's the group that you obtain if, let's do it maybe for n equals 4, but here's a graph. The complete graph on 4 vertices, and I put infinities. And let me call the generators S1, S2, S3, and S4. Then this generates basically the group generated by the SIs subject to the only relation is that each SI squared is the identity. So what are the reduced words here? What are the words that cannot possibly be shortened? Well, there's only one way of shortening a word, which is if you see two consecutive letters that are equal, you take them off. So every word that you have, you can just take out the repeated copies until you're left with a word where there's no two consecutive letters that are equal. Those are the elements of this group. And this is the Freest Group. And this has a name, actually, and you can look it up in the book. I can't remember what it's called. I'll put the name in the notes. I can't remember right now.
And would there be 4 factorial elements in that group?
It's a good exercise. It's not 4 factorial, but exercise how many elements does it have? Well, actually that's not a, you see this thing has infinitely many elements. Like S1, S2, S1, S2, S1. But let's say how many elements of length K. That's a good exercise. Okay. Now, there's another group that I can define, which is kind of at the other extreme, which is if I just don't put any edges anywhere. I just have generators, no edges. So what's this? It's generated by S1, S2, S3, S4, subject to relations that each squared is equal to the identity. And then I have other relations, because remember, when you don't see an edge, you should interpret that as a 2. Okay? So SI, squared is the identity. But what I said here is that saying SI, squared is the identity is equivalent to saying SI, equals SJSI. So what I'm saying is that all the variables commute. So that's a very different group. This is a finite group. And this is the one that you were talking about. So this is a bunch of copies of Z2. Now I did it for 4 vertices, but of course this generalizes to any value of n. Okay? Okay. So these are Coxeter groups. Let's see. Let's talk about an infinite family. Well, no, let's talk about another small one. So let's talk about one like this, but let me just change the number that I put here, m. Well, I won't write down the presentation. I think by now you see how to write down the presentation. But let me write down my claim, which is that if you write down this presentation and you think about this for a little while, you're going to see that this guy is isomorphic to the dihedral group Dm. And you will think about this because this is one of your homework problems. Okay. Homework. So this gives you a nice simple presentation of the dihedral group that maybe you haven't seen before. Okay. Now, let me show you another very nice Coxeter group. And that is, you see there's no end to this. I could just draw any graph and ask for the Coxeter group that I get. But these are somehow some very important ones. What if I just have a path? The graph is a path. So there's 3's here, 2's everywhere else. Okay. So what are the relations here? Well, the relations are, now like I said, when there's no edge, that means Si Sj squared is equal to 1, which means that Si and Sj commute. So when there is no edge, Si and Sj commute. Now, when is there no edge between I and j? Well, there's edges between adjacent ones. So when the difference between I and j is greater than or equal to 2, there's no edge. Okay. So that's the relation that I get. What about consecutive ones? Well, for consecutive ones, what I get is Si plus 1 Si equals Si plus 1 Si plus 1 for I up to n minus 2. Okay. So what I'm going to claim now is that this is a presentation of the symmetric group Sn. Symmetric group. I should tell you, this is an eternal problem for anybody that studies permutations or the symmetric group. Somehow people can't decide what to call the symmetric group, and the book calls it capital Sn. I will too. But just be careful not to confuse the capital Sn, which is the name of the group, with the little s's, which are their generators. Okay. Sometimes you see this also as this. So people come up with funny s's to tell them apart, but I don't know. If I have to grade your homework, I'm going to ask you to stick to this, because I won't be able to read the 40 different versions of this thing. So I'll just use capital Sn. Okay? But be warned that when you see a funny S sub n in papers and books, that might mean the symmetric group. You should look carefully to see if it does. So you will think about this also, because this is also a homework problem. But I'm going to give you an idea of how this works. Now, the idea is that, well, first of all, what is this saying? This is saying I want to think of the symmetric group as being generated by these guys, subject to these relations. And so the first thing I would have to do is take my symmetric group and find out what these special elements should be that generate it. So I should find n minus 1 permutations that generate a symmetric group. Okay. Maybe you guys can think of a good choice for that. So what should Si be? It's basically going to be a 2-cycle or a transposition where all I'm going to do is switch the positions of I and I plus 1. Okay. So then the first thing you have to convince yourself of is that these guys really do generate the whole symmetric group. This is part of your homework, and this is also a question that I posted in the forum, and you should feel free to talk about it there and work it out together, why these elements generate the whole symmetric group. Any permutation can be written as a product of these. Let me just write it in the other conventional notation, which is as the cycle I comma I plus 1. Okay. Well, there's some relations that these guys are supposed to satisfy. Yeah? So this is only going to be a good choice for SI if it satisfies these two equations, right? This one and this one. And so we should really verify that these SI satisfy these things. Okay? Well, how do we do that? The good thing is that we know in this language how to multiply permutations. Yeah? So I won't spoil the fun of doing this for you, actually. I was going to do it, but this is fun, so you should do it yourself. So check that the relations hold. In other words, just multiply these guys, and that means you get to play with braids and check that these relations hold. Okay. You don't, so then you have to prove that still. So then you have to prove that this is it. That the group is just defined by these relations, and that's it. And that's the last step of this proof. This is a very important problem that you should think about and be prepared to talk about it amongst yourselves. Okay? This is a very nice presentation of the symmetric group. This is due to Moore. Okay. Okay. So there's a bunch of examples of Coxeter groups. Let me keep giving you some other families, actually, that we will talk about a little bit more. The point of Coxeter groups and the reason they're so important is because really they appear all over the place, kind of in nature. I mean, in very different areas of mathematics, Coxeter groups just pop up. And there's some very important families of examples. Large families. Okay. So there's one very large family, which is basically just if you, for example, let's say we do it in three-dimensional space. Okay. You pick a plane, and you do this mirror operation that I talked about last time, where you just think that an operation is to take a point and reflect it across that plane perpendicularly. Okay? So that's an operation. And now if you pick a bunch of different planes, you're going to get a bunch of different reflections. And then you can start studying the group generated by these reflections. Okay? Well, any group generated by reflections is a Coxeter group. Okay. And that means that if there's many good reasons to study Coxeter groups, for example, if you're interested in these regular tilings of the plane, if you're interested in studying regular polytopes and classifying them, it's very natural to end up studying these Coxeter groups. And let me just say that this is not only true the way I describe it to you in 3 dimensions, but it's true in higher dimensions. It's true with either linear or affine hyperplanes, if you know what that means. And it's even true in the hyperbolic world. So there's really many different versions of this. So real, affine, hyperbolic. And by the way, I'm hand-waving a little bit, so don't worry if you don't understand what I'm going to say right here. This is just a motivation for this. For the study of this. They appear very naturally. Okay.
Is every Coxeter group really generated by someone?
That's a very good question. So does every Coxeter group arise as reflections? The answer we'll see is in some way yes, but not quite. We'll see. You'll see what I mean by that. But the answer is that really every Coxeter group can be thought of geometrically. So that's one thing. Well, like I said, symmetry groups of regular polytopes. So, in some sense, the people who were discovering the Platonic solids initiated the study of Coxeter groups. They were really studying these symmetries. Okay. And a very important family, which you'll know about one day, is the family of Weyl groups of root systems. And this comes from Lie theory, study of Lie groups, Lie algebras. This is really one of the big motivations to study Coxeter groups, is that they give you a finite way of studying a very big object. And so these are three very good reasons to study them, and we will say more about, I'll tell you more about this one, I'll tell you more about this one, and I will not tell you, well, I'll tell you about root systems, but I won't tell you about Lie theory, just because there's a lot of prerequisites for that. But it's something that I would really encourage you to learn one day, because it's really very beautiful. And you'll see how it plays with this very nicely. Okay? Yeah?
So, I don't know if you said this exactly, so the precise definition of a Coxeter group is a group generated by some elements that satisfy that each of the generators squared is the identity and all the other relations are a product of two generators.
Mm-hmm.
Power.
Yeah, that's what I wrote over there. A Coxeter group is basically something that can be presented as the group of a Coxeter diagram or of a Coxeter matrix. So these are somehow many good reasons to study Coxeter groups. Okay? Now let me go back to a point that Jameson brought up, which is that in giving you this whole list of Coxeter groups, I specified a Coxeter group and a presentation of it as saying, okay, these are generators, and they satisfy certain relations. But an important warning sign, let me put it in red, warning sign. A Coxeter group W can be maybe well, let's say can have different presentations. Can have different presentations as a Coxeter system. So you could have something like W and S and W and S prime, which these are really both Coxeter systems. So Coxeter systems you can have something like this where really the generators are different and the relations are different. For example, you can even have a different number of generators. So you might be able to present a Coxeter group in this way in different versions. And an example, which again is a homework problem, is the dihedral group D6. I think that's the smallest example of a Coxeter group that has two different presentations as Coxeter systems. Okay.
In general, the Coxeter group you get depends on, you can get different Coxeter groups depending on the generator.
Yeah. So
You're saying it's possible for these two things to be isomorphic.
yeah, I mean, so here this is the same group.
Right.
Yeah. So it's possible that you have isomorphic groups, even though you have different Coxeter systems.
Basically not every graph labeled this way.
Right. So it could be that two very different graphs give you the same Coxeter group, basically. That's the point. Okay. Any questions about this? So yeah, go ahead.
Will there be like a classification or set of characteristics of a Coxeter group that will determine what presentation it will yield? Or no? Much like in two matroids being graphical.
We'll see. We'll see that really there's a good way. Somehow there may be a good way and a bad way to present a Coxeter group, and somehow there is really a best way. So we'll talk about what the best way to present a Coxeter group is. Okay. So basically what we did today is I told you what a Coxeter group is, and I gave you a bunch of examples that show you that really this is a subject of importance that appears all over the place, and so really we should be studying these things. Okay. All right. See you guys next time. No, but we normally want to. So generally the very nice, very symmetric Coxeter.